In this video, we discuss the mathematical analysis and modeling of chemical systems, which leads to the formulation of second-order differential equations. Real chemical systems typically require numerous experiments to operate correctly and optimally. One of the key advantages of mathematical modeling is its ability to reduce the number of necessary experiments, particularly those that are costly, complex, or difficult to perform. Mathematical models offer significant benefits in terms of cost, time, safety, and environmental impact compared to purely experimental approaches. Moreover, they help guide the design of relevant experiments, support the collection and interpretation of experimental data, and contribute to achieving the best possible performance in real systems. In an ideal, well-stirred laboratory tank reactor, the saponification of ethyl acetate in the presence of sodium hydroxide occurs under isothermal conditions. The reaction is carried out under conditions that allow it to be approximated as a second-order reaction with respect to ethyl acetate. The reaction rate is defined as the number of moles of ethyl acetate consumed per unit time and per unit volume. In the rate equation, C represents the concentration of ethyl acetate, and K is the reaction rate constant, whose value depends on the reaction temperature. It is assumed that the solution is dilute and that the density remains constant throughout the reaction. For students performing this experiment, it is very important that when starting the process, the reactor be started up in such a way that they can reach steady-state conditions in the shortest possible time, so that they have the opportunity to perform all the steps of the experiment. To analyze the time required to reach steady state, the process is divided into two stages. In the first stage, the reactor of known volume, initially empty, is filled with a feed containing a known concentration of ethyl acetate at a constant volumetric flow rate. During the filling process, the saponification reaction of ethyl acetate occurs simultaneously. In the second stage, once the reactor is completely filled, the outlet valve is opened, and the reactor undergoes a transient period before ultimately reaching steady-state operation. Although, in theory, the time required to reach steady state is infinite, in practice the reactor is considered to have reached steady state when the conversion of ethyl acetate attains 99% of its steady-state value. This level of conversion is within the accuracy limits of the measuring equipment. In this context, CS denotes the theoretical steady-state concentration. To determine the time required to reach practical steady state, the reactor behavior during both stages must be analyzed. Therefore, before addressing the main problem, the first step is to calculate the percentage conversion of ethyl acetate at the end of the first stage, that is, at the moment when the reactor has just been filled. We consider a control volume around the reactor. The presence of an ideal agitator ensures complete mixing within the tank, so the solution remains uniform and homogeneous throughout the entire volume at all times. During the first stage, when the reactor is being filled, the outlet is closed. Therefore, the overall material balance indicates that all material entering the control volume over a time interval delta t accumulates inside the reactor, since there is no outflow. The accumulation is equal to the change in the total mass of material within the reactor over the same time interval. Because the density of the mixture is assumed to be constant, it cancels from both sides of the total material balance equation. The mass balance for the ethyl acetate can be expressed as the sum of input and generation minus the sum of output and consumption equals the accumulation within the control volume. Focusing on ethyl acetate, the mass balance equation simplifies because there is no outlet stream, while ethyl acetate is being consumed by the chemical reaction. Thus, the number of moles of ethyl acetate entering the control volume during the time interval delta t minus the number of moles consumed by the reaction over the same interval is equal to the accumulation. This accumulation corresponds to the difference between the number of moles of ethyl acetate in the control volume at time t plus delta t and at time t. Dividing both sides of the mass balance equations by delta t, and then taking the limit as delta t approaches zero, we use the definition of the derivative to transform discrete difference equations into continuous differential equations. Substituting the reaction rate expression into these balances results in a system of first-order ordinary differential equations. Since the inlet volumetric flow rate is constant, the first differential equation can be readily solved using the initial condition that the reactor is initially empty. The solution shows that the volume of the mixture in the reactor increases linearly with time. Substituting this solution into the second differential equation and performing simple algebraic manipulations further simplifies its form. The result is a first-order, nonlinear ordinary differential equation that describes how the concentration of ethyl acetate varies with time. In systems modeling, it is generally advantageous to use dimensionless variables rather than dimensional independent and dependent variables. One benefit of working with dimensionless variables is that they map the original variables from physical parameter ranges to normalized numerical intervals. This rescaling simplifies the mathematical form of the equations, accelerates their solution, and provides clearer insight into their behavior. A second advantage is error detection. Because all terms in the governing equations must be dimensionless, any inconsistency in the dimensional formulation becomes immediately apparent. Most importantly, the use of dimensionless variables leads to the identification of dimensionless groups and parameters, which have special physical significance in chemical engineering. To convert this differential equation to a dimensionless form, a suitable change of variables is introduced and the chain rule is applied. As a result, the governing equation for the concentration distribution in the reactor is transformed into a dimensionless differential equation that contains only a single dimensionless parameter, the Damkohler number. The Damkohler number is one of the main parameters in the design of chemical reactors. The dimensionless parameter Damkohler is actually a measure of the reaction rate of ethyl acetate relative to its transfer rate in the inlet feed stream. In simple terms, if we want ethyl acetate to have the time required to react in the reactor, then it must have enough time to reside in the reactor. Therefore, we cannot expect the inlet feed to enter the reactor quickly and be converted into product immediately. To produce more product, it is necessary for the materials to spend more time in the reactor. In this sense, the Damkohler number can also be defined as the ratio of the average residence time to the reaction time. The average residence time is the ratio of the reactor volume to the volumetric flow rate of the inlet feed stream. This differential equation is subject to an initial condition stating that the concentration of ethyl acetate is finite at the start of the process. It should be emphasized that this equation is valid only during the first stage, that is, while the reactor is being filled. As can be observed, the equation governing the rate of change of ethyl acetate concentration during the filling stage is a first-order, nonlinear ordinary differential equation. This equation is a particular case of the Riccati differential equation. By introducing an appropriate change of variables, the nonlinear term in the Riccati equation can be eliminated, transforming it into a second-order ordinary differential equation. This transformed equation has a simpler form because it is linear, and therefore is generally preferred over the original nonlinear Riccati equation. Solving the resulting second-order linear differential equation allows us to recover the solution of the original first-order equation. However, a second-order differential equation requires two initial conditions, whereas only one initial condition is directly available. The resolution of this apparent difficulty lies in the specific change of variables employed. In particular, the new variable is defined as the ratio of the derivative of a function f to the function itself, which naturally provides the additional condition required for the solution. In modeling many chemical systems, particularly those expressed in cylindrical coordinates, we frequently encounter differential equations of a standard form. This class of equations is known as Bessel differential equations, and their general solutions are expressed as combinations of Bessel functions. The nature of these solutions depends on the coefficients a, b, and s, while the type of Bessel function is determined by the coefficient c in the differential equation. If the coefficient c is positive, the solutions are Bessel functions of the first kind, denoted by j, and of the y. If c is negative, the solutions are modified Bessel functions of the first kind, I, and of the second kind, k. When the coefficient c is 0, the differential equation reduces to an Euler differential equation, which can be solved straightforwardly. Thus, the type of Bessel function is determined by the coefficient c, whereas the order of the Bessel function depends on a parameter derived from the coefficients a and b. For example, plots of Bessel and modified Bessel functions of order 0 and 1 show that functions of the first kind I and j are finite at the origin, while functions of the second kind k and y are not defined at 0. Bessel functions belong to the family of orthogonal functions. A detailed discussion of orthogonal functions will be provided later in the context of partial differential equations. For now, it suffices to note that the general solution of this class of differential equations is a linear combination of two Bessel functions, whose type and order depend on the coefficients a, b, s, and c. To determine the appropriate Bessel functions, one must first compute the coefficient p, which defines the order of the Bessel function. If p is neither an integer nor 0, the general solution consists of two Bessel functions of the first kind when c greater than 0, and two modified Bessel functions of the first kind when c less than 0. If p is an integer or 0, the general solution includes both Bessel functions of the first and second kinds for c greater than 0, and both modified Bessel functions of the first and second kinds for c less than 0. By returning to the original differential equation and comparing it with the standard form of the Bessel differential equation, the coefficients a, b, and c can be identified, from which the coefficient p is subsequently calculated. Since p is 0 and the coefficient c is negative, the general solution of the differential equation is a linear combination of two modified Bessel functions of order 0, namely I0 of the first kind and k0 of the second kind. Because the value of the function f at the initial point is finite, the coefficient multiplying k0 must be 0, as k0 is not defined at the origin, as evident from its graph. Consequently, the solution of the differential equation simplifies significantly. By differentiating this solution and transforming back to the original variable, the particular solution of the original differential equation is obtained. It is clear from this relationship that as time approaches 0, the functions I0 and I1 approach unity and square root of p, respectively, and therefore y approaches 1. This result is expected, since the first drop of feed entering the reactor has not yet undergone reaction and thus retains the same composition as the incoming feed stream. By evaluating the ethyl acetate concentration as a function of time, at the moment the reactor becomes filled, the dimensionless ethyl acetate concentration is obtained as a function of the Damkohler number. After the completion of the first stage, when the reactor is fully filled, the process enters the second stage. During this stage, the inlet feed flow remains unchanged, while the outlet valve is opened such that the inlet and outlet flow rates are equal. As a result, the volume of material inside the reactor remains constant and equal to the reactor volume. Following an approach entirely analogous to that used previously, a control volume is defined around the reactor, and the mass balance equation for ethyl acetate over a time interval delta T is formulated. By dividing both sides of the mass balance equation by delta T and letting delta T approach zero, the differential equation describing the system during this stage is obtained. Using the dimensionless variables defined earlier, this equation is transformed into a dimensionless form that includes the Damkohler parameter. The initial condition corresponds to the moment at which the reactor becomes filled. This differential equation describes the dynamic behavior of the reactor as it evolves towards steady state. During the transient period, the ethyl acetate concentration changes with time and eventually stabilizes at a steady-state value. At steady state, the time derivative vanishes, and the dynamic differential equation reduces to an algebraic equation, which can be solved to determine the steady-state dimensionless concentration. Among the possible solutions of this algebraic equation, Ys represents the physically meaningful and acceptable solution. Consequently, the differential equation may also be expressed in factorized form. Applying the method of separation of variables, along with partial fraction decomposition of the rational expression into a sum of simpler fractions, followed by integration of simpler terms, using algebraic manipulation and enforcement of the initial condition, yields a relationship that can be used to determine the ethyl acetate concentration at any time. The resulting expression involves logarithmic functions. Since all terms inside the logarithms are positive, absolute values are unnecessary. The resulting equation expresses the ethyl acetate concentration implicitly as a function of time. However, it may also be rearranged to express time explicitly as a function of concentration. It should be noted that both Yf and Ys are functions of the Damkohler number. As previously mentioned, in theory, the time required for the reactor to reach steady state is infinite. In practice, the practical steady state is defined as the point at which the ethyl acetate conversion reaches 99% of its steady state value. This criterion lies within the accuracy limits of the available measuring equipment. Knowing the time-concentration relationship allows determination of the dimensionless time to reach the practical steady state. Based on the problem data, the Damkohler number can be calculated, which in turn allows determination of the ethyl acetate concentration at the moment the reactor is filled, as well as its theoretical steady-state value. Using these results, the practical steady-state conversion concentration can be obtained. Substituting the value of the parameters into the corresponding expression yields the time required to reach the practical steady-state point in dimensionless form, from which the actual time can be calculated. In this analysis, the volumetric flow rate of the feed entering the reactor was fixed, and the corresponding time to reach the practical steady state was obtained. However, no optimization was performed in these calculations, and therefore this result does not represent the minimum possible time. The central question is how to determine the minimum time required to reach the practical steady state while maintaining the same volumetric flow rate during the reactor stabilization stage. In other words, if a shorter startup time is desired, changes must be made to the reactor startup strategy. In the initial analysis, the volumetric flow rate was assumed to be the same in both stages of operation. However, if the volumetric flow rate during the first stage, the filling stage, is allowed to differ from that during the stabilization stage, the time required to reach the practical steady state can be reduced. The problem therefore becomes determining the optimal flow rate during the reactor filling stage that minimizes the time to reach the practical steady state, without altering the feed flow rate during the stabilization stage. To answer this question, we assume that the volumetric flow rate of the input feed in the first stage, meaning the reactor filling stage, is V1. In this case, according to the presented mathematical model, the concentration of ethyl acetate at the moment of filling the reactor is obtained. In this regard, the dimensionless parameter delta is similar to the dimensionless number of the dam cola. After the reactor is filled, the volumetric flow rate of the input feed changes and reaches the value at which the experiment is to be performed. In this case, the changes in the ethyl acetate concentration with time in this stage are determined. As can be seen, the time required to reach the practical steady state point depends on the volumetric flow rate of the feed in the reactor filling stage, meaning V1. We should not forget that the volumetric flow rate of the input feed during the reactor stabilization stage, denoted by V, is known. Consequently, the dam cola number is also known, and therefore both the theoretical and practical steady-state concentrations of ethyl acetate are known. The time required to reach the practical steady-state point is minimized if the logarithmic term becomes 0, or the term inside the logarithm is equal to 1. To achieve this, it is necessary that the value of y1 is equal to the practical steady-state value. In other words, if we want the time required to reach the practical steady state point to be at its minimum, the volumetric flow rate of the input feed during the reactor filling stage must be chosen in such a way that the ethyl acetate concentration at the end of the first stage is equal to the practical steady state concentration of ethyl acetate. Therefore, by determining y1, the parameter delta can be obtained using numerical methods such as the Newton-Raphson method. By determining the delta parameter, calculating the volumetric flow rate of the input feed during the reactor filling stage, meaning V1, is not a problem. In this case, the time required to reach the practical steady state corresponds to the parameter delta, and is shorter than the time obtained previously. Therefore, if the inlet feed flow rate in both the first and second reactor stages is assumed to be the same, the reactor stabilization time for a given volumetric flow rate is known. However, if the feed flow rate in the first stage is a fraction of that in the second stage, this stabilization time can be minimized through optimization. Once the reactor is filled, adjusting the inlet flow rate to a predetermined value allows the reactor to practically reach steady state, after which measurements can be performed on the outlet stream. In other words, if we want to complete all the experiment stages on time, the reactor must be filled at a rate such that at the moment of filling, the ethyl acetate concentration is equal to the practical steady-state concentration, based on the selected volumetric flow rate, in the second stage. Investigating the kinetics of the ethyl acetate saponification reaction is one of the cases where students spend a lot of time performing all the stages of the experiment, and the reason for this is that in most instructions, the method of performing and selecting the experiment parameters is not selected correctly, and no optimization is done in conducting the experiments. This optimization can be done by selecting the volumetric flow rate, the ethyl acetate concentration in the input feed, or the temperature. A change in each of these parameters brings a change in the dam cola number. Therefore, the general method in optimizing this system is to select the dam cola number and determine the delta parameter to reach a practical steady state with the minimum time required. By determining the delta parameter, the unknown parameter can be reached, which can be the volumetric flow rate in the reactor filling stage, the ethyl acetate concentration in the input feed, or the temperature in the reactor. In fact, by choosing the dam cola number as the reactor stabilization parameter, we can reach the delta parameter as the reactor startup parameter, in such a way that the best result, which is to minimize the reactor stabilization time, is achieved. By choosing the Damkohler number, the reactor stabilization point, which is the end of the process, is not in our hands. But how to start the reactor to achieve the desired goal is in our hands. This is the job of a chemical engineer who, by arranging the available elements, achieves the best desired result. I hope that by analyzing this laboratory reactor, we have realized the superiority of the mathematical model for more accuracy in how to conduct experiments, optimally select parameters, and prepare instructions. In the next video, we are going to discuss thermal fins in the topic of heat transfer, and how to achieve the best design for the fin with a mathematical model and optimization.